All right. So, getting into lesson one here of chapter one. We're going to start really getting into, well, what is calculus? And hey, that's the kickoff. What do you think calculus is? Now, you may have different ideas. You know, it's something very more complex math, higher level math, or you might be thinking calculus sounds like torture, sounds like pain. Well, no pain, no gain, right? Kidding. It's not going to be that bad. It'll be just fine. We will do good. You will do good. I am there for you. We're going to get through this. Well, what is calculus? Well, calculus is the mathematics of change, velocities, and accelerations, as well as tangent lines, slopes, areas, volumes, arc lengths, centroids, curvatures, and other concepts. Now, you're probably looking at that going, okay, well, mathematics of change, okay, got it. Velocities, K. Accelerations, we're doing science. Well, there's some science concepts. Tangent lines, slopes, hey, slopes I like. Areas, K. Volumes, arc lengths, centroids. I feel like I heard that in geometry. Curvatures, other concepts that sounds like Bed Bath & Beyond. We don't know what beyond is, but it's something. Really, it's going to be okay. We're going to get into most of this, and when we get there, it'll be fine. We'll go through it. We'll take our time with it. You'll understand it. Don't get overwhelmed yet. Now, pre-calculus, what you've done, you've involved areas, a lot of these areas. You know, we've done change, we've done velocities, accelerations, tangent lines, slopes, areas, volumes. We've done a lot of that stuff in pre-calculus. Well, what's different is all that pre-calculus was static stuff. We were finding average rates of change. You know, it was changing at an even amount. It was a constant amount that it was changing by. Well, calculus is going to get more into dynamics, so those instant rates of change. So as we're accelerating, as that acceleration is changing, how, you know, what is our change in acceleration? You know, we can get into those instant changes. So for example, pre-calculus, we would find the average change of a line. So think their slope is the slope between 2 points. That's that average change between there. Calculus would find that instant rate of change. So as it's curving, say on a parabola, we can find the slope at any point along that curve with calculus. Calculus will have three stages. So calculus starts with pre-calculus, mathematics. So think what you did last year in advanced math. The limit process, which we'll get into this chapter even, and then the actual calculus. So the meat and bones of calculus. So really what we're going to do is we're going to build off those concepts of pre-calculus, so the stuff you did in advanced math, but take it to another level. Now, with calculus, there's two main problems that make up the base of what calculus is. Starting with the tangent line problem. So the tangent line problem is this. If we have a curve going through there, not just a linear equation, but if we have a curve, we want to find what is the slope of that tangent line. So what is that instant slope at whatever point we're at? Now, before what we did is we did the secant line here using slope. We pick 2 points, find how are they changing. Well, what calculus is going to do is we're going to pick this second point so close to this first point that they're pretty much instantaneous to get the instant slope. Now, our point of tangency is at c comma f of c. So a certain point and then the y value of the graph at that point. Now, we would pick a second point, which is c plus change of x. Change of x is just another point a certain distance away, a change of x away. And then c plus change of x inside that function. So whatever this point is, we put it into our function. So it seems more complicated, but it's really not. This is change of x just means at x distance away from our first point. So as far as slope is going to end up being, well, if we use these 2 points, we would use the second one here of f of c plus change of x minus the original f of c. So we always, and I'm off the page, sorry. So we always do our y's on top. Bottoms would be the x's. Well, our second x here is c plus change of x. The original was just c. We would subtract that c away. Well, if we simplify this, we have a minus c and a positive c. That can cancel. And so what we get here is our f of c plus change of x minus f of c over change of x. Now, this should look familiar. If you think back to advanced math, this is our difference quotient. And this is where calculus picks that back up and kind of runs with it for a while. Now, we'll get into other things, but we will use this again here in calculus. But what it's saying is it's that second y minus our original y over how much it's changing, which if we take our x and our x2 minus x1, that is our change of x. Our y2 minus y1, that's our change in y. So that's really what we're doing here, is using that slope formula to set up this difference quotient, and then we'll use that here in calculus. Now, where the limits parts come into this is we want to find the limit, which is basically going to say like however close we need to get in order to say, hey, this is what the slope of that point is. So that limit is really going to be really, really small. We want to be right next to that original point. But the limit is that point in which we're saying, hey, we're close enough to know that, hey, this is what the slope is. And again, we'll get into that a whole lot more here further on in this chapter. But that's what we're talking about here. So, we're going to find the slope of the equation f of x equals x squared. So, dealing with f of x squared, f of x being x squared, we're going to start with the point 1, 1. So, we're going to pick one that's close to it. So, let's say we start at 1.5. Well, 1.5 squared, if we put that in there, so 1.5 squared is going to be 2.25. Now, we could pick one closer and go 1.1. Well, 1.1 squared is going to be 1.21. Well, then we could go 1.01. And we'd be at 1.0201. So, the calculus that we'll do here in the future will take care of picking these points. But these are just to kind of show you some examples of how this is kind of going to go. So, if we find slope starting with this first one, we would do 2.25 minus the original y, which is 1, over 1.5 minus the original x, which was 1. So 1.25 over 0.5, which is 2.5. Then we're going to do it the next one. So now we are 1.21 minus our 1 over 1.1 minus 1. Well, 0.21 over 0.1 would be 2.1. So now if we do it one more time here with our last one, so 1.0201 minus 1 over 1.01 minus 1. So all three of these times we're using this p, the original point, as our original point. These here are going to be our second point to find the slope. So 0.0201 over 0.01, which 1212 would be 2.01. So with this, as we get closer and closer to that original point, you can start to see that, hey, we have a certain number that we're getting closer to as well for our slopes. So in this case, our slope Looks like it's approaching 2. Now, we could keep going with this and keep getting closer and closer with these points, and this over here would keep getting closer and closer to 2. So that's that limit process. So closer and closer to where we hit that limit of saying, hey, we're close enough that we know what it's going towards. Now, the calculus is going to take care of the limit process, but we'll get into that another time. The other part of this is called the area problem, which if I zoom out just a little bit here. So the area problem is finding the area underneath a curve on a graph. So like looking here is we're finding this here, which is an irregular shape. So we don't have a formula like we do for, say, a rectangle or a square. However, what we're going to end up doing is we're going to break that area into these tiny boxes. Now, what calculus is going to do is make this change of x so small that it's practically instantaneous, and we're filling in all of these here gaps and our overlaps. That's going on here. So that's what calculus is going to do. But what we're going to do is I'm going to show you here, if we pick, and the smaller the boxes, the more accurate it's going to be. But we're going to be able to find that area under a curve with what we know already before we even jump into the calculus part. So we're using the region bounded by the graph of x squared from when x is 0 to when x is 1 and that x-axis. So if I drew this out, we're going from 0 here to 1 of this curve. So we're limited with the end here and from 0 what this is under here. Now, we're just going to start by finding four different rectangles. So if we're going from 0 to 1, so 1 minus 0, we're covering 1 unit. And we'll break this into 4 units, so we're going to get 0.25 for each one. So our first mark here at 0.25, second mark at 0.5, and our third mark at 0.75. We're going to break this into rectangles. So the first one, we're going to use the left side for height. So I'm going to call this, well, we'll just leave it as this. We'll just put it now. So L is going to equal. So L is going to be our sum of our left sides. So the left side is the height of the box. This is what we're doing to begin with here. So as you notice, we're going to have some gaps here that we're going to be a little short. So we'll cover that, what happens here in a moment. But for this first box, we would be 0.25 wide, and our height would be 0.25, or actually the left side, 0 squared. Because area is going to be, so base times height. So our base is 0.25, our height here is 0 if we're using the left side. To get our height, we're using our formula, our function of x squared. So plus, so now the next one. So for this box, we're again 0.25 wide, but our height is on this left side of when we're 0.25 squared. Third box, again we're 0.25 wide, but now we are 0.5 squared for our height, plus 0.25 for width. Our last one, we're 0.75 squared. So for this first one, 0 squared is 0, 0 times 0.25 is going to be 0. The next one, if we use our calculator, 0.25 squared times 0.25, we would get plus 0.015625. Next one, 0.5 squared times 0.25 would be 0.625. And our last one here, 0.75 squared times 0.25 would be Oh, I did this wrong. 0.0625. Should be that one. 0.140625. Which, if I add those three up, I end up with 0.765625. Now, the next time I'm going to use the right side. So, like here, this would be the box. Okay. So we're still using x squared for our height. We're still 0.25 wide. So 0.25 times, well, the right side is 0.25 squared plus 0.25. Again, the second box, the right side now is 0.5 squared plus the next one here would be 0.75 squared plus our last one of 0.25 times our height of 1 squared. Well, a lot of these we've done already. So we would get, the first one here is like the second one of the one above. So 0.015625 and then 0.0625 plus 0.140625. Now, the only one we'll have to do is this last one, which 1 squared is 1 times 0.25 would be 0.25. So really what I'm going to do is add 0.25 to my last one, and I'd be at 1.0156. From there. I'm going to add these two together. And divide it by 2. And we would get, so left side of 0.765625 plus, I feel like this is really high. Let's go back and double check our math, all right? So here's another one of those moments where I do make mistakes and I realized what I did here. So for my first one, I'll have the 0.015 plus the 0.0625 plus the 0.14065, which is 0.21875. That's a lot better. And then if we add 0.25 to that, we get 0.46875 there. So add the two together. So 0.21875 plus 0.46875, and we'll divide it by 2. So 0.2 plus the 0.46. If we divide that by 2, we end up with 0.34375, which is going to be our approximation for the area, so units squared of under that curve. So it's around that 0.3. Now, calculus will be able to go through and fine tune that. So say we broke it into 10 boxes, well now we're 0.1 each, and that should close those overlaps. So that'll make it even more fine-tuned. So the more boxes you can do, the more accurate it's going to be. which makes sense. Now, that's it for this lesson. Let me know if you have any questions, comments, concerns. Remember, you can always pause. Need time to write stuff down, you can always rewind it or move the dot back and rewatch something if you need to, if you missed something. Otherwise, until next time, we'll talk to you later.